Welcome everyone, and today we are going to discuss complex integration. And the first thing is coming, that is, a region is called simple connected and multi connected if some region is shunked to a certain point without losing its area is called simple connected, and if the region does not shrink to a point, here you can see there is another curve C2, so it does not shrink to a point, is called a multi-connected region. Okay, so if this curve is shrunk to a point, then it is called simple connected, and if does not, then it is called multi-connected. Next, we are going to discuss about Cauchy's integral theorem. You can write the definition. I am telling. If a function f of z is analytic, if a function f of z is analytic in a certain region, R, bounded by a curve C, then we always have closed integration C f of z dz, that is equals to 0. This is known as Cauchy's integral theorem. This is valid both for simple connected and multi-connected region. So the next thing is the proof of this Cauchy's integral theorem. So let f of z is equal to u function of x and y plus I v function of x and y, and closed integration c f of z dz is equal to closed integration c u plus iv into dx plus I dy. Clear? Now multiplying this into this, you can write closed integration u dx minus v dy plus I closed integration c v dx plus u dy. Okay. Now from Green's theorem, we know that closed integration m dx plus n dy, that is equals to surface integration delta n by delta x minus delta m by delta y dx dy. Okay. Now using this into this, you can write closed integration f of z dz, that is equals to surface integration minus del u by del y minus del v by del x, that is into dx dy plus I surface integration del u by del x minus del v by del y. Okay. Now from the previous class we are discussing about the Cauchy-Riemann equation. Now using this equation you can easily see that both the part is going to 0. So we are getting here and using CR equation, this gives close integration C f of z dz that is equals to 0. So it is proved. Okay, very simple proof. So we are basically using Green's theorem and Cauchy-Riemann equation. Now in the next part we are going to discuss the consequence of Cauchy's integral theorem. Consequence of Cauchy's integral theorem. Okay, I have just write the short form of Cauchy's integral theorem. Okay, so number 1. If a region is such that it is given by this, say A, B, C, C and D, and the whole curve is known as capital C. Okay, it is the imaginary axis and it is the real axis. So if a function f of z is analytic bounded by region C, then from Cauchy's integral theorem we know that close integration C f of z dz that is equals to 0, right? So from this we can also write integration a b c d a b c c d a. So it is closed loop. F of z dz should also equals to 0 from this to this. Clear? Now this can be further written as integration a b and c f of z dz plus integration c d a f of z dz that is equals to 0, right? We can write it further, integration a b c f of z dz that is equals to integration a c d, okay, adc, sorry, adc, it is adc, it should be negative, adc f of z dz. Okay, now what we can see from here, now you can see that integration a to c is independent of path, that is via this way abc or adc the integration should be remains same. Remember the integration value cda, that is in this way, is turned to be negative, that is cda from the opposite side. Okay, so it is independent of what you can write, that is integration a to c f of z integration a to c f of z dz is path independent, is path independent. Okay, now We are moving towards the second consequence. So this is the first consequence. Now we are talking about the second consequence. So what does the second consequence gives? If a region is such that this, okay, A, B, C, D, and it is E, F, and then it is G, H, I. So two regions are here. One is C1 and another is C2. So two curves are there. The inside curve is C2 and the outside curve is C1. This is the imaginary axis and this is the real axis. Now from Cauchy's integral theorem we can easily write from starting from point A. So A, B, C, D, E, F, G, H, I, A. A, B, C, D, E, F, G, H, I, A. F of Z should equals to 0. Okay. Now considering the upper circular part, that is integration C1 F of Z dz. Okay, so this part is cancel out, the upper part, that is G H I. Okay, now plus integration C2 now integration C2, that is F of Z dz. Remember the sign of this curve C1 and C2 are opposite because these are coming from this, so it is anti-clockwise and this is clockwise C2. Okay, so C1 is anti-clockwise and C2 is clockwise. This is clockwise direction. This is clockwise direction. Okay, and two parts are there, integration E to F and A to B. Let us write plus integration A to B F of Z dz plus integration E to F F of Z dz, that is equals to 0. So from this to this we can easily write this. So this part gives this and this part gives this, and C1 for this and C2 for this. Okay, now we can easily see that this part and this part are cancel out because this gives the same value in opposite direction. So this should be 0. Okay, so what we are getting now? So integration C1 anti-clockwise F of Z dz is equals to clockwise direction C2 F of Z dz. That means the value of the upper curve, that is C1, in anti-clockwise direction is equal to the value of the lower curve in same direction, that is anti-clockwise direction. So these two consequences are very important to find out some integral values, some complex integral values. Okay, now let us discuss some problems regarding the complex integration or Cauchy's integral theorem. Okay. evaluate close integration c dz by z minus z naught, where c is a circle with z equals to z0 outside and inside. So the value of this integration you have to find out when c is a curve, that is circle, when z equals to z0 is outside and another point is inside. So we can draw the Argand diagram from the first case 1. So this is a region C, say C, and it is connected, and let the radius should be epsilon. Okay, it is the imaginary and it is the real part, and z0 is outside. So from Cauchy's integral theorem, f of z dz is equal to 0 inside all over the point. Inside the region, if the function is analytic, then it gives 0 from Cauchy's integral theorem. Okay, we have find it out. So it is 0 when the point z0 is outside. Now the next interesting thing is when the point z0 is inside. So we are drawing two circles inside the curve, the z0, and we are drawing the two curves. One is for the region and one is for the z0 point. Okay. Now in this case, the integration should be calculated as integration dz by z minus z naught, that is equals to integration, say the curve name is C1, say the curve name is for C1, so it is C1 integration dz by z minus z naught. This can be easily done by the Cauchy's integral theorem consequence number 2. Okay, so no doubt is there. Now putting z minus z0 is equal to epsilon e to the power I theta. So dz is equal to, from here, so dz is equal to epsilon I e to the power I theta. Now putting this value into the above integration, we can easily see this is from 0 to 2 pi, and the above part epsilon I e to the power I theta d theta is equal to epsilon e to the power I theta gives 2 pi I. So when the point z equals to z0 is inside the curve, we have to draw a circle. Okay, then we have to find it out by this way. If the point is outside, then it is easily 0 from Cauchy's integral theorem. Okay.